Assalamu alaikum students. Welcome back to our another online session for the course Digital Logic Design. And this session basically covers the concept of the logic simplification by using kmaps. So in this session we will try to learn how we're going to simplify our Boolean expressions so that we can implement our Boolean functions and systems by using minimal number of resources. So to start with, let's see the content we will covering in today's session. We will be discussing the k-maps, basically how we're going to construct the maps for the two literal system, for the three literal system, and for the four literal system. And then we'll go through the rules which we will follow in order to simplify our expressions, and we'll go through some of the examples so that we can have practice of the k-maps, and uh, so that any boolean function that has been given to you, you can easily simplify that boolean expression. So we've got both the options. Either we can simplify our Boolean expressions by using Boolean algebra, or we can use some simplification techniques, and kmaps is one of the simplification techniques from the many which we can use in order to simplify our expressions. Well, as far as the reference readings and acknowledgements are concerned, we are at chapter number 3 of the book Digital Design with Introduction to Verilog HTML. So to start with, first of all, let us see our revise. What are the contents which we have studied in our previous session? We have seen that we can implement our digital system mathematically by use of the Boolean function, and we have also discussed that we can represent the combination of inputs and outputs with the help of truth table, and we can also implement the logic diagram from the truth table or from the Boolean function, and we've also discussed the timing diagrams as well. So in order to simplify the expression, first of all, let us first see the need why we need to simplify our expression. If we have an expression uh, in a standard form or canonical form, why we need to simplify the expression. So first of all, these mapping techniques or the k-map technique results in our Boolean function that is always in a standard form rather than in a canonical form of expression. So why do we need to simplify the expression? The most important thing is the simplification of the process is required in order to the first reason is to optimize our resources. So we have to optimize our resources so that we can implement the same Boolean function by use of the minimum number of resources. So what is the benefit of reducing the resources? The main benefit is the cost element. So we can implement the same Boolean function with same functionality with minimal cost. The second benefit is the power consumption in the terms of power consumption of the system. And the third benefit is the increase in performance of the system, or we can say that performance optimization. So let us first discuss the maps, how we're going to generate the k maps. That is basically a graphical method in order to simplify our expression. So we have to construct the maps basically. So what are the basic elements of the map? So we'll go through with the example. So with the example of the three literal system and two literal system and four literal system. So starting with the two literal system, if we've got a Boolean function, for example, we've got a Boolean function f of x, y. So basically we've got x and y that are two literal. So total number of combinations that we are covering in this system are 2 raised to power 2, that are the 4 combinations. And similarly, if I've got a system of the three literal, f of x, y, z, and in that particular case we've got total number of combinations that can be represented in a truth table that are 2 raised power 3 that are 8. And similarly, with the increase in the literals, the number of combinations are also increased. In the previous session, we have learned that how we're going to generate a truth table and how we're going to represent any particular Boolean function and the response of the system. And we've discussed two systems. One was in a canonical form of expression and the other was in a standard form of expression. And for the canonical form of expression, we've discussed about the sum of min terms and product of max terms. And we have seen that if you are considering sum of min terms, then we'll consider those min terms that are contributing 1 to the output of the system. And for the product of max term, we will consider those max terms that contribute 0 to the output of the system. Then we've learned the method that how we're going to generate the min terms and max terms and how we're going to implement the Boolean functions by using the min terms or the max terms only. So basically that prior information is required in order to understand the maps. So to start with the maps, basically if you've got the two literal systems, so our map should be capable enough to handle or to represent all the four possible combinations. So how the map is being distributed? The map is being distributed in such a way that each combination is being represented have a proper representation in the map. So to start with, let us assume that we've got x and y. So x and y are the let's assume these are the two inputs, and the combination of the inputs are 0 0, 0 1, 1 0, and 1 1. And let us assume that the response of the system is being represented as, for example, represented as z. Okay, so let us consider the response equals to 1 1 1 and 0. As far as the standard expression is concerned, in terms of min terms, we've got z equals x prime y prime, or x into y prime, or x into y. So our map should also contains or have the representation of these four terms. So our map is basically distributed in terms of cells. So we've got a map that has been distributed in terms of cell, and cell is the individual representation representing a min term or a max term. So if you've got two literal system, we've got four cells. So map is distributed into four cells or the four sections. Okay, so we'll represent the inputs of the literals as rows and columns of the map. For example, this bar basically represents that either we are representing row with which literal, and we are representing column with which literal. So for example, I've written here as this is x and this is y, which means that these rows are represented the value of x and this y represents the value of columns represents the value of y. So what could possibly the value of x? X can be 0, x can be 1. Similarly, y can be 0, y can be 1. So this is basically considered to be a cell. This thing or one block or one section is basically known to be a cell, and each cell will have its proper representation regarding the Boolean function. So for example, the first cell, if we look at this first cell that will have the value x equals to 0, I'm talking about this cell. Let me highlight this with this. For this cell that has been highlighted with green color, we've got the value of x that is equal to 0. X is 0 here in this cell, and y is also 0 here in this cell. So that cell has a value that is equal to x equals to 0, y equals to 0. The next cell has a value x equals to 0, y equals to 1. The next row has the value 1 0 and 1 1. So either we can place our min terms here in these cells, or we can place our max terms here in this cell. So what we have to do is first of all we have to place our response of the system here in these respected cells. So let us place the response, and let me erase these. So for x equals to 0, y equals to 0, the output z basically are represented in the cell. So z equals to 1. So we'll write 1 here. For 0, 1, the output is 0. We'll write 0 here. For 1, 0, the output is 1. We'll write 1 here. And for 1, 1, the output is 1. So we'll write 1 in this cell. So this is the way we have constructed a cell, a map of the two literals, and we have placed our Boolean function in those respected cells. Now let us go to the literal of the three variables. So we've got the possible number of combinations that are 8 in that particular system. So let us first see how we're going to represent in the map basically, and let us go through an example. For example, we've got a Boolean function z equals f of a, b and c, a, b and c, and that is equal to 0, 1, 4, 5 and 7. So this is min term number 0, this is 1, this is 4, this is 5th, and this is 7th. So if we generate a truth table from this expression, the truth table would be A, B and C here. Oops, let me erase that. C here, and the output is Z basically. And the combinations are represented as that are 0, 0, 0, 0, 0, 1. This is 1, 0, 1, 0. This is 0, 1, 1. This is 1, 0, 0. This is 1, 0, 1. Next is 1, 1 and 0, and the last combination is 1, 1 and 1. And the system that has been given to you is here. This is 1, this is 1, this is 1, this is 1, and this is 1, and all the other combinations are basically 0. Now in order to represent that in a map, basically we will have a map that has the 8 cells in it. So let us consider a map that has been distributed into 8 cells. And the inputs that have been represented as A is being represented as the rows, and B and C are represented in terms of columns. And the value of A and B and C are here 0 and 1, and here we've got 0, 0, 0, 1. The next value is 1, 0, no, the next value is 1, 1, and the last value is 1, 0. This is the placement that has been represented in the map, so we have to follow the same placement as we are using kmap. So the ordering is not symmetrical or systematic or in a sequential order. So you have to remember that this thing is not equal, the third column is not equal to 1, 0, it's equal to 1, 1. So the first cell basically has a value 0, 0, 0, then 0, 0, 1, then 0, 1, 1, and then 0, 1, 0, then 1, 0, 0, the second row, 1, 0, 1, 1, 1, 1, and 1, 1, 0. Now let us place this function here in the map. So for the 0, 0, 0, the z is 1, so we place 1 here. For 0, 0, 1, the z is 1, we place 1 here. For 0, 1, 0, we place 0 here. For 0, 1, 1, it's 0, we place 0 here. For 1, 0, 0, it's 1, so we place 1 here. For 1, 0, 1, it's 1, we place 1 here. For 1, 1, 0, it's 0 here. And for 1, 1, 1, it's 1 here. Okay, so this is the way that we'll place our Boolean function into the map, and we'll represent our cells with their respected value. Okay, so let us go to the map of the four literal. So in that particular case, for example, we've got a function z equals f of k, l, m, and n, and that function is basically equals to 1, 3, 4, 6, 7, 9, 11, and 12, for example. Okay, so as far as the truth table is concerned, we've got a truth table of the 16 entry. So you can represent that truth table, but right now I'm just implementing the map, and we're going to see how we can directly implement that function into the map or place the values into the maps. And this is the function that has been represented in the sum of min terms. So all those min terms, min term number 1, 3, 4, 6, 7, 9, 11, and 12 are contributing 1 to the output, where z is equal to 1. For all the other combinations that are missing in the Boolean function, the output is 0. Now our map should have the 16 possible entries. So the map is basically distributed into 4 cross 4 cell array, and two literals are represented as row entries and two literals are represented as column entries. Now the possible values of these cells are 0, 0 for the rows, 0, 1, 1, 1, and 1, 0, where first literal is basically this is k and this is l. Similarly, for the columns, we've got 0, 0, 0, 1, 1, 1, and 1, 0. So with this representation, now we have to place the values here. So if you see that the first min term is 1, so the binary value of 1 is basically that is 0, 0, 0, 1, in which k equals to 0. This is k, this is l, this is m, and this is n. So for the k and l is 0, 0, so we are on the first row, and the column is 0, 1. This is the column, so the value here is basically 1. Okay, now coming to the second min term, that is basically that is 0, 0, 1, 1. This is k and l value, and this is m and n value. So we are at the row 0, 0, and the column is basically that is 1, 1, so we've got 1 here. Then we've got the term 4. So the binary value for the 4 is basically 0, 1, 0, 0. So this is k and l, so we are at this row 0, 1, and for the column that is 0, 0, so we'll place 1 here. Next is 6, this is 6, next is 7, this is 7, then next is 9, this is 9, next is 11. So 11, for the 11 we've got the binary value that is equal to 1011. So 10 is basically our row and 11 is our column. This is 11. Then we've got 12. So the binary value of the 12 is 1100. So this is K and L. So we are at this row and the column is 00. While the rest of the entries in the map are basically 0. 0. This is 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 0 and this is 0. Well, I hope so. Now you are able to generate the maps of the two literals, of the three literals, and of the four literals. We are not discussing the map for the five literals right now, but we maybe in future we can discuss the five literal implementation by using kmaps. So I think so that is sufficient for you. In the next session, basically we will discuss the rules and regulations that are being followed in order to implement or in order to simplify our expression. The first thing is to generate the map. So in the today's session we have learned that how we're going to generate the map, and the next thing is, once we have generated the map, the next thing is to simplify our expressions by using those standard rules and principles that are being defined in the kmaps terms. So that's all for today's session. So take care. We will meet next week and we will discuss some implementation examples, and after that we will switch to the combinational logic design.